Hey everybody, it's time to talk about some exploratory data analysis. And for clarity, we're talking about a single numeric variable. So that's the kind of data we have in our data set. Okay, so um, the two basic questions we want to ask is what's the shape? Typically, we'll be looking for a bell-shaped distribution. There are other shapes that we do see in an elementary probability and statistics course. But after we know the shape, then we're going to ask about skew and or outliers. Okay. Um, so we are going to look at the descriptive statistics. Second, we're going to look at the histogram and density plots, and then box plot actually help answer both questions because they check for outliers. They've got an outlier checker. Not only is it a picture of the 5-number summary, um, it helps show both the shape and detects outliers. Okay, so we tend to do the descriptive statistics first and then come back to the outliers question. And we do need the descriptive statistics to help identify the outliers. So let's take a look at this. All right. Now, before we start doing the descriptives, let's look at the different shapes. And there you go on the right of the screen, you'll see the top left in that graphic is approximately normal. And you can see that not only is it bell-shaped, it's approximately symmetric too. About the same number of smaller bars on each side. Are there slight differences? Yes, but it's an approximately symmetric, approximately normal or bell-shaped distribution. Um, Top right is another bell shape. It's clearly bell-shaped. But now we have more bars that are nearly the same height, about 4 bars there that are nearly the same height. But again, the data is stacking up in the middle and then tails to the left and the right. Okay, so the tail of a distribution, of course, is the part that's tailing off to the left or to the right. And we have tails in this distribution as well. They're not quite as well defined as they are on the left, but it's clearly a bell-shaped distribution. And here's where we end up with skewed right. This is what we mean by skew, where the tail to the right is much, much greater than the tail to the left. It's a much longer tail to the right. And same thing when we have skewed to the left, much longer tail to the left than to the right. Approximately uniform. A uniform distribution is where all the probabilities are the same, like a dice roll, right? Where the probability of rolling a 1, 2, 3, 4, 5, or 6 is identical, right? They're all 1/6. So then the distribution, the bars in that distribution would be approximately the same height. And then we have bimodal. Okay, so sometimes the data stacks up around two main values. So in a bell-shaped distribution, of course, the most popular values, the mode, are going to be in the middle, right? But sometimes we have two modes, and so we have data that'll stack up around two different values. Okay, so those are the basic shapes that we're looking for. And let's move on. All right. So there are some cool things that we know about a skewed right distribution. Not only is the longer tail to the right, it means that outliers generally are on the right. Well, why? Well, again, the major portion of the data set is here. So typical values in the data set, I've just circled there in red. So to be an extreme data point in this data set, one that's not like the typical values in the data set, you have to be out to the right. There's just not room on the left to be far enough away from the center of the data set, right? So it's just much, 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 much more likely that we're going to have outliers to the right. And one reason that outliers are called influential data points is because they influence the mean. And if I have skew and outliers to the right, generally speaking, that means the mean is greater than the median. Are there some weird little data sets where that may not be true? Yes, but typically if we have skew to the right, if we have the majority of outliers to the right, then the mean is going to be greater than the median. And it probably won't surprise you to find, sorry, to find that the same is true for skewed left, right? Again, the outliers tend to lie to the left. The outliers are influential data points. They have like a gravitational pull on the mean, but not the median. And that makes sense if you think about a data set um, of average summer earnings for UNG students. You have a class filled with 20 UNG students, and then Oprah Winfrey walks in. Well, her summer 2024 salary was probably higher than all of the UNG students. And let's just say that the mean and the median before Oprah walked in was about $5,000 for the summer. And then Oprah walks in and she made $20 million in the summer of 2024 or whatever it might be. Well, what happens to the mean? Well, the mean jumps to the right. And if she made $20 million and there are 21 people in the data set, now it looks like everybody made about $1 million summer earnings. Well, again, the median is still near the 5,000. So the median doesn't move as much, but the mean jumps towards the outlier, right? Again, that's why they're called influential data points, and that's why when we have skew to the left, the mean gets pulled to the left, and the mean will be less than the median. And when we have outliers on the right, the mean gets pulled to the outliers. Again, the outliers exert kind of like this gravitational pull on the mean, and the mean jumps towards the outliers. Okay, so this is true in skewed data sets, whether skewed left or skewed right. Skewed right, the mean is typically greater than the median. Skewed left, the mean is typically less than the median. The same thing is true in reverse. If I can't see a graph, but I can see the descriptive statistics and can see that the mean is significantly different than the median, then I am suspecting skew and outliers. I'm expecting that, okay? And if we are looking at the descriptive statistics to get a preview, we use what I call Rob's rule of thumb. Why? Because after looking at literally hundreds and hundreds of data sets, I came up with this. It's just what I kept seeing. And I've shared this with some colleagues, and a couple of my colleagues have tested it out, and they concur that it works. Does it work 100% of the time? No, that's why it's a rule of thumb, not a law. But if a distribution has the mean and the median, the difference between them is more than 1/10 of a standard deviation, start to expect skew and outliers. Okay? And so just as an example, suppose your mean is 8 and your median is 6. Okay, so the mean and median are 2 units apart. The standard deviation is 3, so 1/10 of a standard deviation, right? And this is why I chose it, because you just have to move the decimal place, right? To divide the standard deviation by 10, right? It's just a move of the decimal place. All right. Well, this distance, right? If the mean is 8 and the median is 6, the distance between the mean and the median is 2. 1/10 of a standard deviation is 0.3. So do we expect skew or outliers? Of course we do. And which way do we expect it? Well, the mean is above the median, right? It is bigger than the median, so we're expecting skew to the right. We're expecting outliers to the right and skew to the right. Like I said, this works more than 90% of the time. There are a few times when it doesn't work. That's why we call it a rule of thumb. But this is just a way, if we're only looking at the descriptives, to tell what might be happening in the histogram or the density plot, or when we look at the box plot, what we'll see. Okay. And actually, I want to stop there and jump into the notebook and actually do some calculations. Okay, so to get us started, I went ahead and loaded some data sets. So let's go ahead and execute the first couple code blocks, right? And this is loaded perfectionism data and anxiety and birth weight data from the babies. data set, and elevation data from U.S. airports. Okay, that's going to be in feet above sea level. All right, so we have them all loaded now. And it says display the standard descriptives and the 5-number summary for the data, for the perfectionism data and for the anxiety data. Okay? And what I'm going to do is I'm going to pause the video and I'm going to go copy paste that standard block where we use the cat function. And there are a couple of places to get it. I'm just going to the last section, the last notebook that we did because we did it in there. Okay, so I just opened the S0 notebook that we used last time, and we had done the standard descriptives for the sleep variable. So I'm just going to change a few things. Right now, this is going to be the perfectionism data. So I'm going to change a little bit of the text, right? And I'm going to change the, instead of S for our sleep variable, I'm going to change that to perf for the perfectionism variable. And I think I've changed everything I need to. And there you go. The standard descriptives, mean 108, standard deviation 17. All right. And then the question is, do we expect skew and outliers? Okay. And notice down at the very bottom, right, the mean and the median are printed out next to each other in the 5-number summary. Again, the mean isn't necessarily part of the 5-number summary, but it's included. And they're 0.7 units apart. Notice that the standard deviation is 17.25, so the mean and the median are not more than 1.7 units apart. They're only 0.7 units apart. So we would generally not expect skew and outliers in this case, right? So, and then it also asks for the same question, but with anxiety. What am I going to do? I'm going to copy paste the perfectionism, right? And I'm going to change perfectionism to anxiety in all of these places. Sorry. So in the print parts, I've got it, and I see I had typed that in. That was a mistake. Trying to get the indents the same there. Okay. And then A and X is the data set variable name. And there we go, the standard descriptives for anxiety. And notice here that the mean and the median are 1.747 units apart. So almost 1.5 units. The standard deviation is 9.5. So the standard deviation, a tenth of a standard deviation, would be about 0.95. Here we would say, yes, we're expecting skew and outliers. So no for perfectionism, yes for anxiety in terms of expecting skew and outliers. Okay? So that's how we calculate descriptive statistics. And again, they can give a preview. We can't determine skew and outliers until we see the histogram or density plot or box plot and so forth, but we can at least get an idea. Okay, so jumping back to the PowerPoint, right, when it comes to the histograms, that's the traditional thing that statisticians have used for 100 years to determine shape. Density plot is an excellent addition to our toolkit. It's a little more granular, so it better shows some things like skew or whether or not it's bimodal data. What are heavy tails? Heavy tails is where a distribution has more outliers than a normal bell-shaped distribution should have. It's fairly common for real world data just to have a few more outliers than we would suspect for a normal bell-shaped data set. So that's what we mean by heavy tails. And again, the density plot may show that, it may not, but it's more likely to show it than the histogram. So you'll notice as we transition into data checks for our t-tests and ANOVA that I tend to use density plots. Histograms can be used. I find the density plot a little more granular, a little more detailed, and so then it's a little bit more helpful. If you are using histograms, remember breaks equals 10 is the default, but we can try things like 10, 20, 30 in terms of breaks to do the baby bear just right kind of thing. Too few bars in the histograms, we just can't detect any shape at all. We just see a couple bars. If we have too many bars in the histogram, we get this bumpy mess, and we really can't see anything either. So we want to adjust the breaks, and it might be 15, or it might be 35, or it might be 5. But we're going to try values like 10, 20, 30, and values near that, and that's generally going to work. And then the density plot doesn't really have any options that we have to worry about. We just make it. So let's jump into the notebook again. Let's see what we've got. Produce a histogram for the anxiety data set. Okay. And it's just hist and anx. And that will do it. And if we get a good picture, which that isn't bad, we don't have to worry about the breaks. I'm just going to type it in. Breaks equals 20. Again, the standard's about 10. I don't know that it's exactly 10, but it's about 10. And breaks, what is this doing? Well, so these bars are supposed to be based on equally spaced intervals along the x-axis, okay? And a higher number of breaks means a higher number of intervals, so the intervals are shorter, they're narrower, okay? And as breaks increases, I get more intervals and more bars. As breaks decrease, I get less intervals and less bars. Okay, so that's what the breaks is talking about. And for breaks equals 20, let's run this. And you see I'm getting, it starts to get pretty busy pretty fast, right? And it's still showing a little bit. I'm trying to go up to where, yeah, at some point there's just not getting any more detailed despite the fact we have a lot more bars. We can go back to 5. Again, 5 is too few. Are we starting to see a bell shape? Yes, but we don't have enough bars in that histogram. So breaks of about 10 works for this one. Okay, and again, that was the standard histogram. It's hard to tell a difference between the standard and 10. I'm not going to count right this second, but they look to be the same. Okay, and then it says density plot for the weight data set. So we do plot parentheses and then density parentheses, and then we can do the weight data. Okay, and you can see here we definitely have a bell-shaped distribution. We have a slightly longer tail to the left, so we might have a little bit of a skew to the left. All right. And one thing you should get used to is the titles. The titles are not hard, and there's a lot of ways that they're similar across all our different types. And one thing we do, the overall title is called main, and I can say for a title, density plot, baby weight. And then I kind of have gibberish as my x-axis label down here. So we have a sample size of 1174, and I'm not exactly sure what the bandwidth means. All right, but I have this option to create an X label, and it's just comma xlab equals, and I'm just going to say weight. And I think it's in ounces. I'll have to think about that and look at the values in just a second. But XLab, weight in ounces. And again, it just is going to clean up the look of the plot just a little bit. Yeah, 16 ounces, the 180 ounces then would be a little more than 10 pounds, but we don't have very many babies that are that big. These are much smaller babies to the left. So yeah, weight in ounces. Ounces seems to be the right units for this. Okay. So do you have to always put labels on your plots? No, but a lot of times it's helpful to remember what exactly it is that you're seeing. Okay. And we'll do box plots in just a second. Jumping in, so the box plot is a visualization of the 5-number summary, but the box plot includes detection for outliers. And we'll go over how that formula works in just a second. But the rectangle in a box plot covers the middle 50% of the data. So we can see what a typical, not exactly an average, but what a typical value in the data set looks like. And then, of course, because it has, well, in grade school, they call it a box and whisker plot, and the whiskers are the length of the tails, essentially. So we're able to see if one tail is much longer and if there's skew. So the box plot really is helpful. It lets us see if there's skew. It lets us see if there's outliers. It shows us where the middle 50% of the data is, and it's absolutely amazing. So let's do it for perfectionism and anxiety. All right, so it's just box plot is the command, and we can do perf, cha-ching. And I want to point out that even though we were told by Rob's rule of thumb not to expect skew and outliers, there's a slight skew to the left, perhaps, not much of one, but there is an outlier to the left. And I will point out that it's not a very significant outlier. It's somewhat close to that fence. So we only have one outlier, and it wasn't all that extreme. So again, in that case, Rob's rule of thumb doesn't quite work. I will admit, why did I pick a tenth of a standard deviation? Well, I picked a number that was easy to divide by, right? And should it be, 11th, a 12th, a ninth, an eighth? I don't know. Perhaps one of those other fractions might be better. But a tenth is real easy to calculate and evaluate, and it works a lot of the time. It's about right. Okay, but it missed it in this case, honestly, and it does sometimes. That does happen. Okay, so that's our box plot for perfectionism, and were we supposed to do anxiety? Yes. Okay, so box plot angst, and you'll notice we were expecting skew and outliers to the right, based on what we had seen in the descriptive statistics. And there it is, an outlier to the right. So a box plot, and you can see a longer tail to the right. This one is definitely skewed because the right tail is much, much longer than the left tail. So we're able to judge and assess the skew and outliers from a box plot really well. Okay, and jumping back in, right, we're going to talk about how we identify outliers. And there's two ways to do it. There's a numerical way, and there's a way that I'm calling graphical, but it's basically based on the box plot. What method does the box plot use to determine outliers? So if we're going to identify outliers numerically, we're using the mean and the standard deviation. And our rule is any data point that's more than 2 standard deviations away from the mean is going to be an outlier. I will admit that this works in a small data set, let's say sample size of 200 or less. If the sample size is bigger, say we're talking about 1,000 or 2,000 or 2,500 in our sample, we're going to have to use a larger number. Maybe 3 standard deviations would be more appropriate for a larger data set. And we can talk about that later. But for the moment, let's just assume we've got a small data set and we'll use 2 standard deviations from the mean. Okay, now the way the box plot calculates outliers is it calculates an upper fence and a lower fence. And remember that Q1 and Q3 are the quartiles, right? Q1 is the 25th percentile, Q3 is the 75th percentile. So the IQR, the interquartile range, is Q3 minus Q1. It's just the height of that box in the box plot. Okay? And the lower fence, you go to the 25th percentile and you subtract 1.5 IQRs. You draw a fence. Any point that goes beyond the fence is considered an outlier. Same for the upper fence. You start at Q3 and you add 1.5 IQRs. Draw a fence there, and any value that goes beyond that counts as an outlier. Now, technically, the box plot, if it lands on the fence, it's not considered an outlier. So the standard box plot, if you're on the fence, you're not an outlier. And I don't know what your mom thought. My mom probably wouldn't have been happy if she told me not to go outside the yard and I was on the fence. But the box plot rule is if you're on the fence, you're still in the yard. You're still not an outlier. Okay, so let's check that out. Let's jump into our notebook. Okay, and how do we find outliers? Okay. Well, the first thing we can do for perfectionism is we can get the mean, right? And we can add 2 standard deviations to it, times 2, and we'll take the standard deviation of the mean. Okay, so there you go. Sorry. What is going on there? Oh, I'm sorry. Perf, in the standard deviation of perf. Okay, so there is the mean plus 2 standard deviations, and any data point that's bigger than that is going to be considered an outlier. Okay, so what do? Look what happens when I do perf greater than this value. Okay, this is a kind of like a question mark. And perf is a vector, and for every single value in the vector, it's going to evaluate whether that value is bigger than the mean plus 2 standard deviations. And you see all these trues and falses? There's 130 of them or so. Okay? And so all the truths are outliers, all the falses are not. And then it turns out that I can do this. I just do sum. Boom. And we've found 3 outliers above, if that makes sense. Why? Because we did greater than. And what are we going to do? Well, we're going to go sum. But now we're going to go the other way. We're going to do below. And maybe I should do it in the other. Maybe I should do below and above, so that makes more sense. And less than the below, the lower cutoff, and greater than the upper cutoff. Oh, and there are 3 below and 3 above. That is interesting. Again, this is another reason that our Rob's rule of thumb wasn't working so well. In this way of checking for outliers, we have an equal number of outliers on both sides. So they're balancing each other out, right? If you have 3 outliers on the left, exerting pressure on the gravitational pull on the mean, but you got 3 on the right that are also pulling on the mean, they're kind of balancing out. So the mean hasn't moved that far away from the center. Okay? And then I can also calculate an upper fence. How? Well, I need to know, let me do this. I need to know the summary for the perfectionism variable. Why? Well, I need these quartiles, right? So my upper fence, let's see, underscore fence, is going to be equal to, and by the way, you see me using the left arrow, right, instead of equal to. That's just how R will often understand the equal to. And there's a slight nuance about the difference, but it is good form in R to use that left arrow instead of an equal to when we're assigning a value to upper fence. But what is the upper fence? Well, the upper fence, that's going to be on the high side. I'm going to take Q3. Well, Q3 is 120. And then I'm going to add 1.5 times the IQR. Well, what is the IQR? Remember, the IQR is Q3 minus Q1, so 120 minus 97. All right, and then the upper fence is 120 plus 1.5 IQRs, right? And the lower fence is going to be 109 minus, oops, 1.5 IQRs. And I'm going to have to type these out so that they show up. And there we go. And then the question is there any data point above 154.5? Right? So what do? I can just do the sum of perf greater than 154.5. And I can do the sum of perf less than 74.5. Okay, and so this is showing 3 outliers to the left and none to the right. But again, just showing you how these calculations work. Okay, and then what I didn't do was I haven't done it for anxiety, but it's the same thing, right? If I want to do anxiety, I'm doing the sum of the perf is greater, excuse me, is less than 2 standard deviations below the mean. And we're summing up the number of values in the perfect data set. I'm sorry, this is supposed to be the anxiety data set. So let me jump back here and make sure that's the anxiety data set. And notice that we get 5 outliers to the right and 0 to the left. And if I do summary of ANCs, then my third quartile is 44, and my first quartile is 30, right? And then the upper fence is starting at the 44 and going up 1.5 IQRs, and the lower fence starts with the 30 and then goes down 1.5 IQRs. So there are my fences, and we're checking to see how many of these values are above 65 and how many of these values are below 9. That seems a little wonky. Oh, it's anxiety, not perfectionism. That's the problem. Okay. Those are two very different scales. Perfectionism has a lot of values above 100. That's why we're seeing that. There we go. There we go. Now we're getting the one outlier that we saw in the actual box plot. So there you go. There's the way to actually calculate outliers. And it turns out that we can use a greater than or less than and the summation function to count the number of outliers. Okay, so that is going to be helpful for us. And then conduct an exploratory data analysis on the birth weight data. Okay, well, the first thing I'm going to do is I'm going to grab the standard descriptives. Sorry. Get up here. And I'm going to copy paste the standard descriptives in. But I'm going to make sure that I change, that's not birth, that's how you spell birth, weight. And I'm going to change birth weight down there. And then weight. And then weight. And there we go. Great. Okay. And just quickly comparing the mean and the median, notice that they're only 0.5 apart. They're very close. Why? Because the standard deviation is 18.3. No, am I? Okay. Yeah. So This is the right data set. I'm sorry, that's what I was checking. Okay. But there don't appear to be skew and outliers according to Rob's rule of thumb. Okay, so what are we going to do? I'm going to look at a density plot. And at the moment, I'm not going to mess around with the titles. And we have a nice bell-shaped distribution. Do we have a little skew to the left? A slight. There's a slight skew to the left. And I'm going to look at a box plot. Okay, so box plot, weight. And notice there are some outliers to the left and some outliers to the right. We're balancing out a good bit, but there are a few more outliers to the left. So this longer tail to the left makes sense. Why? Well, we're seeing a few more outliers down below than we saw up above. So yes, there is a slight skew to the left. But overall, what's our analysis of this? Right? Our analysis is approximately normal, right? Which means bell-shaped. Those are synonyms. All right, approximately normal and skewed, and I'm going to say slightly to the left. It's not massively skewed. It would be fine to say it's skewed to the left and leave the word slightly off of there, but I'll just let you know this isn't a huge amount of skew, okay? And then it says to conduct an exploratory data analysis on the airport elevation data, which is L. Okay, so let's take our standard descriptives. I'm going to copy paste those again because this is a really nice summary with the cat function. Everything prints out nicely, and I just have to change. So we're going to do airport elevation, and these are all airports in the United States. There are also airports and heliports, so there's a lot. And the variable name is EL. Sorry, and then EL. And one more time. Okay. And notice that the average elevation of airports and heliports in the country are about 1,100 feet above sea level, which, by the way, is approximately the elevation in Dahlonega. And there is an airport in Dahlonega, and it's about that elevation. So we're pretty average in that sense. Notice that the mean and the median are quite far apart. But the standard deviation is 1,400, so 145. Do we expect skew and outliers? And the answer would be yes. This appears to be a skewed right data set, right? Because the mean is near 614 units higher, and a tenth of the standard deviation would be about 145. So yeah, we're gonna definitely think this. Rob's rule of thumb is going to predict this is pretty much skewed to the right. Plot density L. And this is why we're using the density plot instead of the box plot. Will the box plot show this as well? No, it's just not as granular, not as detailed. And what's going on? We have a little bit of a second mode, a little bit of bimodal action is starting to appear. Would I call this bimodal? And I'm going to say almost, right? This is almost enough to call it bimodal. So our analysis will be approximately bell-shaped and bimodal. Why do I say bell-shaped? There is a slight evidence of a tail to the left. There is strong evidence of a tail to the right. And I have the tallest bars in the histogram, or the mass, the center mass of the data, right, piling up with a tail on either side. So I'm going to call that approximately normal. Okay, it's definitely skewed right. So what am I going to say for my analysis? I'm going to say approximately normal with some bimodality, right? Is it fully bimodal? No, but it's almost bimodal. So I'm going to say some bimodality and strong skew to the right. And I hope it's clear why there's a strong skew to the right. I mean, it's massive in terms of length compared to the tail on the left, right? Is there a little bit of tail to the left? A little bit, right? Barely enough to call this approximately normal. That's tough. But there's just enough of a tail to the left that we can call it that. And then we have this massive tail to the right. So this is definitely skewed right data that's just about normal and starting to be bimodal. Okay, and I just want to say that analysis of these data set shapes and their attributes is some art and not all science. In other words, there are gray areas, right? And this is why I wanted to show this example, right? Because there are some interesting features of this distribution. It's pretty much bell-shaped, kinda. It's starting to be bimodal. It does have strong skew to the right. So there is some gray area here. There's a little more art than science. On a test or a quiz, I'm going to try to leave it less open-ended, if that makes sense. I hope to make it more clear, give you a data set where the shape is easy to determine. So hopefully that will help you, not be freaking out about, oh my gosh, how am I going to know exactly what he wants on the test or a quiz? Well, I'm going to try to put a data set on the test or a quiz where it's much, 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 much more clear than it was in this example. But this example is good because that's how statistics works in the real world. As I like to say, real world statistics can be real messy.